We're going to look now at radical functions, which is just any function that has a variable in the radicand, that's under the root sign. Could be a square root, a cube root, fourth root, anything like that's a radical function. So let's just begin by looking at our basic square root function, y equals the square root of x, which we've looked at before, but let's just review its main features. We know that with square roots or fourth roots or sixth roots, we can only root 0 and positive values. So our domain is x is greater than or equal to 0. And our outputs, the symbol, the square root symbol, represents the positive square root, so our range is positive values and 0. And just to plot this graph quickly, some points we can use. The lowest value of x we can use is 0, and the square root of 0 is 0, so our graph starts there. Some other convenient values, the square root of 1 is 1, the square root of 4 is 2, square root of 9 is 3. I'm just picking the convenient values, plotting them, and reminding myself that this graph increases with time, but it's increasing at a decreasing rate. It's continuing to go up, but it goes up at a slower and slower rate over time. Another thing we can say about a square root function is that it's the inverse of a quadratic function, y equals x squared. If we switch x and y in our parabola, we get x equals y squared. And if we isolate y, we get y is plus or minus root x. And remember that when relations are inverses of one another, they're reflections of each other about the line y equals x. So on my calculator, I'm going to graph root x and x squared, as well as the line y equals x, which is the line that they reflect across. And there's my square root graph. Here's my parabola. And there's the reflection line y equals x coming. And of course, the parabola doesn't reflect the left side of the parabola because we're not taking plus or minus when we isolate y. We're just taking the positive square root part, which is the top part. And by the way, this basic square root graph, the shape of a basic fourth root graph, sixth root graph, eighth root graph would be similar because all of those would have the same domain restriction. You can't root negative values with an even index. And the graph would look similar, as I say. The points would be a little bit different, but the basic shape would be essentially the same with an even indexed radical function. In terms of an odd indexed radical function, such as a cube root of x, we know that we can cube root negative values, so our domain here will be all reals. And the outputs will be all reals as well, as we're going to see when we just build a little bit of a table here. The cube root of 0 is 0. The cube root of 1 is 1, and the cube root of negative 1 is negative 1. And the next convenient value is 8, the cube root of 8 is 2, and the cube root of negative 8 is negative 2. And plot these points. Get a graph that looks like that. And the cube root graph is the inverse of the cubic graph, y equals x cubed. If we look at that on the calculator, the cube root graph, x cubed, and our reflection line y equals x. We can see a reflection of the two graphs across the line y equals x. And this basic shape radical function will be what you get whenever you have an index that's odd on a radical. So a fifth root, seventh root, ninth root of x graph would look similarly. The points would change a bit, but the basic shape would be the same with the same domain and range. Now that we have our basic radical functions established, we can of course graph more complex functions with transformations. So I have a square root radical here that's got a variety of transformations involved, And let's just remind ourselves of the basic transformed form for a function. Y equals a times f b x minus c plus d. Each of a, b, c, and d do different transformations. And so let's just set up our function here in this format. I'm going to need to factor out the -2 to separate the translations and reflections and stretches happening on the x. So f of x would be 3 square root -2 x minus 2 minus 1. Now I can of course graph transformations step by step, one transformation at a time, or using mapping notation. I am going to do a variety. I'm going to do both just as a review of this. So we're going to start with y equals square root of x. Those are our core points, x comma y. There's our core points on our square root graph. And let's do one transformation at a time. So let's do 3 times root x, which we know is going to be a vertical stretch by a factor of 3, which is going to multiply our original y values by 3. So while our y values are 3 times as much as they are currently, and this will stay at 0. Next I'm going to move into the negative that's in the x, and we know that that's going to reflect the graph across the y-axis. The x will switch sign. Graph reflects across the y-axis. Then we're going to apply the 2 that's multiplied by the x, replacing with x. 2x means that our x's have to be half the size to compensate, and that's going to horizontally stretch or compress the graph by a half. So while our x values are going to half, x of 0, half is 0, half of -1 is -1/2, half of -4 is -2. So my graph now looks like so. Replacing x with x minus 2 shifts the graph 2 units to the right, so the first coordinate increases by 2, and the -1 translates the graph down 1. It causes our y values to lose 1 unit. And so my black graph here, 2 units over 1 down, lands me here. 2 units over and 1 down lands me there. And this point, 2 units over and 1 unit lands me there. And my graph is a curve like so. So just in terms of using my mapping notation to do this, I wouldn't necessarily have to graph step by step. If I just did my mapping notation and notice that my points have gone from xy to this. And so let's just check our original coordinates out with the mapping notation. 0, 0. If x was 0 and y was 0, when we plug that in, we would get 2, -1, which I can see as a point on my new graph. Good. 1, 1 was another core point we started with. -1/2 plus 2 would be 1.5, and y1 would be, make that 2, and 1.5 comma 2, yes, that's a point on my new graph. And similarly with 4, 2, 4 over 2 is 2, -2 plus 2 is 0, and y is 2, making that 5, and yes, 0, 5 is a point on the graph, so I could use my mapping notation. Let's just check this out with the calculator. So I'm just going to type in my original function, 3 square root of negative 2x plus 4 minus 1 graph, and I can see that my graph looks similar to this. The only thing is that on the calculator it looks like the graph starts at the x-axis when it really should be starting here at 2, negative 1. I've confirmed that already. Let's just, if we trace on the calculator and put in x equals 2, let's see what it says. It does say negative 1. So yeah, the graph is actually starting here and going up, even though it doesn't quite look like it. That's why you've got to be careful with calculators, because depending on the graph, sometimes you may not see this sort of the correct features of what's happening. So in this case, the graph is starting at negative, is starting here, not at the x-axis.